Hi, I'm the founder and CEO of UAndor. Today I'm going to present our medical digital twin prototype built specifically for the Medical Med CDID. This tool is a scenario-driven decision environment for evaluating how military medical systems perform under operational constraints. It allows planners to construct realistic casualty flow scenarios, apply conditions like limited evacuation, degraded logistics, and terrain constraints, and then compute how those functions interact across the system. Instead of analyzing demand, treatment, movement, and sustainment separately, it brings them together into a single model that shows how systems behave over time and under uncertainty. For Armory Med CDID, this provides a practical way to test concepts, compare alternatives, and understand how different decisions affect outcomes like backlog, readiness, and system degradation. Let me start in the scenario library. This is the entry point to the system. The first feature here is that scenarios are template-based and reusable. Each of these represent a different operational condition: baseline, mass casualty, urban, denied logistics. So instead of just building everything from scratch, a planner can start from a known problem and adjust it. You can also import scenarios directly from JSON. That's important because it allows integration with external systems. A scenario can be generated from another tool, exported from an analysis pipeline, or shared across teams, and then loaded directly into this environment. That makes this portable and interoperable instead of looking into a single workflow. You can also duplicate and edit scenarios. This gives you the ability to take a baseline case, create a variation, and compare outcomes side by side. That's critical for experimentation and concept development. I'm going to open the baseline scenario in the builder. Now I'm in the scenario builder. This is the authoring environment. The main feature here is that users define the system directly. You can add friendly units, enemy units, medical nodes, logistic nodes, and hazardous nodes, all in a single interface. Each of these properties have objects that have capacity, protection, mobility that feed into the model. So instead of working with abstract inputs, you're configuring a system with real components. Another key feature here is that everything is editable in place. I can select any object, change its attribute, test different configurations of the same system without building the scenario. And because this is map backed, placement matters. Distance, relative position, and exposure all affect how the system performs when it's evaluated. Next, I'm going to open the workbench. Now the system takes that scenario, evaluates it. The workbench is where the analysis happens. The key feature here is runtime tuning. These sliders allow you to adjust major constraints in real time: casualty rate, evacuation availability, medical capacity, logistics availability, coordination efficiency, and environmental factors. That means you can test how the system responds to changing conditions without rebuilding the scenario. Now I'm going to run a Monte Carlo. This allows the core analysis capability. Monte Carlo runs the systems repeatedly with variation with those inputs and produces a distribution of outcomes. This allows you to understand not what just happens, but how sensitive the system is to change. On the right side, you can see the distribution of outcomes. That's the risk profile of the system under uncertainty. Across the top are the results. These are the computed values: backlog, preventative death, supply shortfall, latency, and readiness. These are derived from how the system behaves, not entered by the user. Another key feature is time-based playback. I'm going to play the scenario. This allows you to see how system evolves over time, not just the final state. You can see where demand begins to exceed capacity, when the backlog starts to accumulate, and when the system transitions from stable to degraded. That's critical because most of the failures in these systems happen over time, not instantaneously. Another feature is the inspector panel. This shows the current system state, the primary bottleneck, and the current conditions at any point in time. So instead of seeing numbers, you can understand what's driving the system. There's also a recommendations panel. This translates outputs into actionable guidance, whether to increase evacuation, redistribute supply, or adjust treatment capacity. So the system is not just describing the problem, it's helping inform decisions. So overall, the system provides scenario creation, scenario import and sharing, real-time parameter tuning, time-based analysis, uncertainty analysis through Monte Carlo, and decision support through system state and recommendations.